Good afternoon, everybody, or maybe in some countries it's the morning, then good morning to you. Today we talk about isoelectric focusing, and we have a second title, The Sharper the Better, because the bands in isoelectric focusing should be razor sharp if it works right. Okay, let me just start with the next slide. And I want to give you first an overview about what we are talking this afternoon. First, I will give a short introduction into the basics of isoelectric focusing, as a reminder maybe. Then we have a concern on isoelectric focusing with the Carrier Ampholytes. We talk about vertical isoelectric focusing gels, and we talk about horizontal isoelectric focusing gels. Which method is better? Where are the differences? I also will very briefly introduce the technology how to generate titration curves of your proteins, and in the end we talk about immobilized pH gradients as well, which are mainly used for high resolution 2D electrophoresis. And we have also products for this. These are immobilized pH gradient strips. We will also very briefly introduce these. Yeah, proteins. Isoelectric focusing you can do only with amphoteric compounds, and proteins are amphoteric compounds, as you certainly know, because they are composed of the amino acids, which contain carboxylic buffering groups and amino buffering groups. So when you place protein into basic environment, as shown on the right up here, you will get a deprotonation of the carboxylic groups, which means you have negative charges on the protein, and so in total the protein has negative net charge. If you do the opposite and place them into acidic environment, you get protonation of the amino groups, which means that you have positive charges on the molecule, so you have positive net charges. Now if you modify the pH, and if you come to the very special, very certain pH, very special for each protein, where the negative and the positive charges are equal, then you have reached the isoelectric point. The isoelectric point is the pH value where the positive and the negative charges are just equal. So you have a net charge of 0. That means such a molecule will not migrate in the electric field anymore. Every protein differs from another one because of the isoelectric points. They're very, very different, very individually. And the explanation is because proteins are so complexly shaped. You see here an example. As you see the differences of proteins are by the primary structure, secondary structure, tertiary structure, and quaternary structures. And the different isoelectric points, or the well-defined isoelectric points, is not the only characteristicum. You also have a characteristic net charge for each protein. This is often forgotten. The net charge curve is found here on the lower right. If you plot the charges of a protein on a scale of pH values, you will get a very individually shaped, very typical net charge curves as well. The place where the net charge curve cuts the x-axis, this is the isoelectric point. This is where you have no net charge of 0. There is a technique which is really very simple to perform. This is titration curve analysis, and I will almost at the end of this presentation show you how you can generate the titration curves of your proteins in your lab very easily. I hope you see the animation on the right side, which should show how isoelectric focusing works. So you should optimally find the position of your sample application. This is particularly important when you have relatively complex samples under native conditions. There you should find the best place where to apply the sample. I will later on comment on this also, how to find out where is the best place to apply the sample. So when you now apply your protein mixture at a certain pH, part of the proteins will be positively charged, the others will be negatively charged. So in the electric field, positively charged migrate towards the anode electrophoretically, positively, sorry, towards the cathode electrophoretically, and the negatively charged towards the anode, but only until they reach their isoelectric point, because there they lose their charges, they have a charge of 0, so they cannot migrate anymore. Now optimally, an isoelectric focusing gel has very large pore sizes, because you want to avoid sieving or retardation of the proteins, because this is only separation according to the charges. That means that when a protein has reached its isoelectric point, does not mean that it will stay there. It can diffuse away from it, and but this is no problem in isoelectric focusing, because once a protein diffuses away from its isoelectric point, it will immediately gain a charge again, and then will, by the electric field, be pulled back to the isoelectric point. This is the so-called focusing effect, and this is a really efficient bend sharpening effect, which gives us one of the big benefits of isoelectric focusing, because it acts against diffusion automatically. Now, how can you generate a pH gradient? The first method, which is now possible since the invention of the Carrier Ampholytes in 1966, is the Carrier Ampholite based concept. You see here I have named the SERVA light. This is our product, and actually SERVA light is the most famous product of SERVA, I believe. It's on the market since more than 30 or 35 years already, very successfully. So what are Carrier Ampholytes? This is a mixture of a few hundred homologues of amphoteric buffers. Amphoteric buffers with their own isoelectric points reaching from pH 3 up to pH 10. These are relatively small molecules, and they have a very special feature, namely that they have a high buffering capacity, high buffering power at their own isoelectric point, and a high electric conductivity as well as at their isoelectric point. This is differentiating them from naturally occurring amphoteric compounds like peptides and amino acids, because these natural amino acids and peptides do not buffer at their isoelectric point. So that means that Carrier Ampholytes have to be synthetically produced, and of course the homologues should have about the same concentration and should be enough in each pH region, and so on and so on. So when you have this mixture added to your gel polymerization solution, or you soak a gel in the cocktail of Carrier Ampholytes, they are first, of course, in their natural mixture. So you can measure a mean pH value of, let's say, if you want to create a pH gradient from 3 to 10, so the mean pH value will be about 6.5 to 7. That means that the basic Carrier Ampholytes, those with more amino groups, will be positively charged, and the acidic Carrier Ampholytes, those with the more carboxylic groups, will be negatively charged. Now when you apply an electric field, the positively charged Carrier Ampholytes migrate towards the cathode, negatively ones towards the anode, and because they have such a high buffering capacity, they will buffer each against each other and automatically build a pH gradient. I have also tried to make a little animation here where you can see how a pH gradient develops out of such a mixture in the influence of the electric field. And here you can now apply your proteins for isoelectric focusing. There are a few very important parameters you should always be aware of in isoelectric focusing. First of all, as I mentioned already, the pore size of the gels should be relatively large, like 5% T in a polyacrylamide gel, but there are also people who are running agarose gel isoelectric focusing, even larger pore sizes, quite successfully. We do not have enough time to talk about agarose gels for isoelectric focusing. If you have special questions, you're invited to place them on our script board, and I can answer these questions in the end of the presentation. Next is you need high voltages. Because you need high field strengths. You need very high electric field strengths to achieve these focusing effect, because close to the isoelectric point, the net charge of the molecules is very low. You can see that at the when you look at the net charge curve, close to the net charge is very low. So you need a high electric field to get close to the isoelectric point. That means that optimally you should have a power supply delivering up to, like, let's say 2,000, 3,000 volts for 10 centimeter or 15 centimeter separation distance. Also, the temperature is very important, also often forgotten, that the isoelectric points of the carrier ampholytes, but also of peptides and of proteins, of amino acids, are highly dependent on the temperature. So by shifting the temperature by a few degrees, you can also shift the isoelectric point of your proteins, and you get even the effect that proteins are changing their position within the electropherogram if you don't care. So temperature is very important, and if you want to define an isoelectric point, always do that together with a temperature where it has been measured. The sample application. I mentioned this already, that for complex native samples it can be very important to find the optimal pH position in the pH gradient. And you need to find that out. I will show you a little bit later how to do that. Here. And you can also run isoelectric focusing under denaturing conditions, namely when you prepare the sample with urea and when you have a high molar urea in the gel matrix, it must be above 7 molar. Usually the people are using 7 to 8 molar urea in the gel, and then you get denaturing conditions. Then you usually use a higher temperature for separation because you want to avoid the urea is crystallizing during the separation. Yeah, so isoelectric focusing has a few reasons, a few benefits why it's done so in so many labs. First of all, you can use it for measurement of isoelectric points, but with respect to the temperature. This is very important. You get a very high resolution because these focusing effect, because these very sharp bands, you can detect a lot of proteins in a highly complex mixture by isoelectric focusing. And you have native conditions. So you can really, for many enzymes, still measure or see enzyme activities, biological activities after isoelectric focusing. There is a so-called seismogram detection techniques, for instance. It's really easy to perform on horizontal gel layer sample application. All that is very simple to perform. So in routine analysis, no problem to run isoelectric focusing. It is also suitable for preparative applications, namely because towards the end of the separation, the conductivity in the gel is getting quite low because the carrier ampholytes are no longer charged or very lowly charged only, so there is not very much electric current running anymore, and so you don't precipitate proteins. It does not overheat. And it is the ideal separation technique for two-dimensional separation. When you have to separate highly complex samples, you can combine this with the STS electrophoresis for molecular size determination. So you have two completely independent, completely orthogonal parameters for the separation. So now I want to compare horizontal system and vertical system for isoelectric focusing. So in horizontal gels, you can use gels without any pockets, but we have, that's unique, also gels with pockets there for application, or sample wells for application of the samples. Here you see it's polymerized on a film support. And the advantages of a horizontal system is you can easily use that with film-back gels. This is particularly an advantage when you have gels with large pore sizes, because they can easily break or tear during staining. But when they are mechanically supported by a film, they don't have that problems. You can apply high voltages easily because you don't need big buffer volumes, big buffer tanks, so you can easily apply a few thousand volts without any electric shock hazard. You get a very exact temperature control because here you cool the gel directly with a cooling plate and not indirectly through the electrode solutions. I like you do it in a vertical system. And you have the choice of the sample application position. Now, in this case, with the sample wells, it's already defined, but there are most of the gels in the market, they have a smooth surface, and you can apply the samples on the optimal place where you want. Come back to this in a moment. And you can pre-polymerize the gels and wash them, dry them, and you can rehydrate them with urea. So it's possible to have a ready-made gel for isoelectric focusing, which is rehydrated with urea short before use, because I'm sure you know, you cannot supply ready-made gels containing urea because in solution urea is not very stable, so you can maximum have that overnight. Otherwise you produce such a lot of isocyanate that you get very high background conductivity, and you also kill your proteins by carbomilations. So where are the advantages of the vertical system? Of course, there must be also some advantages because we have them also in ready-made form. So this is a cassette of our vertical gels. But the major advantage is you can run them on much simpler equipment and there are much less costs generated. But the problem is temperature control and all these other positive advantages are no longer here. But there we know a lot of cases where people are very happy with the vertical isoelectric focusing gels. So we here we introduce also the products that we can offer for this. For instance, the Carrier Ampholytes, the SERVA lights, already mentioned in the beginning. Then we have ready-made vertical gels in these cassettes, which I showed you already. We have the so-called pre-coats. These are ultra-thin ready-made gels on film support, which are either 15 microns or 150 microns or 300 microns thin. These gels are available with different pH gradients, but also in a blank form, so you can equilibrate them in urea and Carrier Ampholytes when you need urea in the gel. Then we have the family of the FocusGels. These are ready-made isoelectric focusing gels, which are produced in a different way. They are pre-polymerized, washed, dried, and then rehydrated in the Carrier Ampholyte cocktail. There are also different pH gradients available, and this is also available as a CleanGel isoelectric focusing gel. This is rehydratable in urea Carrier Ampholyte solution short before use. And there are the blue strips. These are immobilized pH gradients, mainly used for the, or almost exclusively used for high resolution 2D electrophoresis. Here you see a few pictures of the products, the SERVA lights, but you should remember SERVA is not only an electrophoresis company, we are also a fine chemicals company, so we can offer all the other stuff too, like high quality acrylamide and PIS and in already pre-weighed solutions, and we have the PRIMET, the ammonium persulfate, urea, and what have you, what all you need for running isoelectric focusing. Also the film support, we make the film support ourselves, the gel fix, you can make your own gels. We also have gel casters for vertical systems and gel casters for horizontal systems if you prefer to make the gels yourself. But we also, as mentioned, have ready-made gels. Now, for the vertical, we also have a very easy to use chamber, which we have just introduced not too long ago. We call it PRIME because it brings premium resolution in mini gel electrophoresis. And here you can see how easy it is to clamp a ready-made cassette into the system. You can run 1 or 2 gels at a time, and you have to, that's important in a vertical system, you have to fill that with the 2 electrode buffers, the anodal and the cathodal buffer. Otherwise you have no connection to the electrodes. So this is how a result of such a gel looks like. So these are vertical isoelectric focusing in mini gel format, which means the cassettes are 10 times 10 centimeters, gel is 8 times 8 centimeter inside. They are available in the pH range 3 to 10. You can use a standard mini gel apparatus or that one I showed you in a slide ago. We also have a starter kit which combines the gels and the electrode solutions, and you can order the electrode solutions separately, as you see here. Here I show you something completely new. This is what we just introduced into the market, our new horizontal chamber, which is a highly developed system now for running horizontal gels. You see a drawer here, and so you pull out the cooling plate and you can apply the gel, apply the electrode lid, and run the separation under dark conditions, which is a huge benefit, for instance, when you have fluorescence labeled proteins. But also you have now a space where you can put your power supply, or you can also stack several of these chambers one on top of each other and put the power supply on top of them, so you can really save a lot of space and have a very efficient new system. You can use it for isoelectric focusing, as is our topic today, but also for native page, SDS page, 2D electrophoresis. Here you see the drawer pulled out with the electrode lid. Here you see the aluminum oxide cooling plate, which gives our excellent cooling temperature transfer. You see the anodal, cathodal electrode, and these are adjustable electrodes. You see, for the different positions you would need them for isoelectric focusing, SDS electrophoresis, 2D electrophoresis for different gel sizes. Yeah, when you want to find out where is the optimum position for placing your samples, you should probably take the panes and make a step trial test, and then remember where was the best position for placing your sample, where you have the least precipitations and the best bend pattern. The pre-coats, you remember these very thin gels are run with electrode strips. This is the classical method in horizontal techniques, and the electrode strip at the acidic and the anodal side, but this will be the acidic side of the gradient, is soaked with an acid, could be 0.5% phosphoric acid, for instance, and on the cathodal side you soak the strip either with a base like sodium hydroxide or with a mixture of Carrier Ampholytes, depends on the pH gradient that you are on. If you want to know more details, you can ask me, I can tell you more in the end. Here you see some examples from food analysis. They are all stained with SERVA violet, and I have to tell you, among the organic dyes, the most efficient and highest sensitive staining of isoelectric focusing bands are really done with the SERVA violet. That is better than Kumasi dyes, Comasi R or Comasi G. So on the left you see cheese extract, and the right you see meat separated. Here you see that you can use the isoelectric focusing technique also for quantitative measurements. Here somebody has tried to measure how much pork was placed into a sausage in a beef sausage. This can be quite important to test this, and you see down to a few percent you can really measure with a densitometer. You need good staining and a good densitometer how much pork percentage is in the beef sausage. Also for plant cultivar testing, plant seed cultivar testing, they are used a lot, like maize cultivars, potatoes, and wheat. They are all stained with SERVA violet, as you might see here. The focus gels are slightly different. They are thicker. They are 0.65, so 650 microns thick. We offer these thicker gels for those who need higher buffer capacity in the gel, higher capacity also for protein loads. For instance, also when you have high salt content in the sample or high protein content in the sample, these are more forgiving. They are available with a smooth surface, but also with sample wells placed on optimized positions for some applications, and you have still the choice to apply them with the sample wells towards the anode. There you have acidic application, or towards the cathode, there you have cathodal application. I should not forget to mention that there are two possibilities how to apply the sample. Either you first run your isoelectric focusing gel without sample until the pH gradient has established, and then you apply your samples, or you run your sample from the beginning while the pH gradient starts to develop. This is dependent also on the sample. So I know from experience, I would say in most of the cases it's better to apply the sample already in the beginning, because this is the phase where you have more current, and so you get a more efficient transport of the proteins in the gels. Here you see another potato gel stained with Comasi that was in a CleanGel Isoelectric Focusing soaked with Carrier Ampholytes short before use. For gel rehydration, you use a tray, and there you can soak the urea Carrier Ampholyte mixture into the dry gel matrix by placing the gel with a dried surface down and placing them on an orbital shaker. So it's not a shaker, it's an only orbital, only on horizontal plane shaking, and so you can within 1 to 2 hours get a 7 to 8 molar urea gel without any problems. You usually use like 50 milliliters in excess of the solution for 25 times 10 centimeter gel, which will become 0.65 millimeter thick after rehydration. Here you see an example, 8 molar urea containing gel for separation of caseins. Here you see the drawer of the cooling plate of the chamber again. There is the gel on the film support, and here these are the sample wells, in this case arranged to the anodal side. You see here's the cathodal, here's the anodal side. Here the sample is applied in that moment. Here you see an application which is very important, isoelectric focusing of cerebrospinal fluid and serum for the detection of oligoclonal immunoglobulins. This is done in a clinical area where patient serum and patient cerebrospinal fluid are separated next to each other, and then you see additional bands in the cerebrospinal fluid, indication of multiple sclerosis, and this is realized here. The staining here is very, very sensitive. That's the most sensitive we know for focusing gels. The ammoniacalic silver staining, which we would always recommend to use for isoelectric focusing gels. Much more efficient, much better than normal silver nitrate staining. Titration curve analysis. I promised you in the beginning I will shortly show you how this can be done. Here you are using such a horizontal layer gel which contains an impolymerized sample well, a long sample well, so to say, a slot. And first you run an isoelectric focusing without samples. Then you turn the gel around by 90 degrees, apply the sample, and then you place the cathode here and the anode here. So the cathode here is the anode here. Now you have the electric field perpendicular to the pH gradient in the gel. And at the position where you have acidic pH, the proteins will migrate very fast towards the cathode because they are highly positively charged. The opposite is the case in the basic area. They are negatively charged and migrate to the anode, depending on the net charges of the different proteins which they have, and where they stay in the slot, there is the isoelectric point. And now, in this way, you can really generate your titration curves, and you see already for these marker proteins that the shapes of them are very, very individual, different, and you can read out of this a lot of information which might be useful in your lab. There is the alternative of casting immobilized pH gradients. This is done with a gradient maker, and here you introduce carboxylic and tertiary amino groups into the gel matrix itself. So you copolymerize them. You need these acrylamide derivatives to make this mixture acidic solution, a basic solution, and then you have the gradient fixed into the matrix and it cannot move anymore. It's not influenced by different salt contents or protein contents. You will always get absolutely straight iso-pH lines. This is very important to know because this is the only electrophoresis technique where you can cut a gel into narrow strips and apply the sample without any edge effects. So only immobilized pH gradient gels can do this, that you can run electrophoresis in a strip without any edge effects. And therefore we have these IPG strips. Here you see a picture of different strip lengths that we offer, 7 up to 24 centimeters, different gradients, very wide gradients, linear and non-linear, and very narrow gradients for special applications. And the last thing is in detection, there are a few things which are special in isoelectric focusing. First of all, if you want to detect the proteins in the gel, you need to fix them with 20% trichloroacetic acid. There is no other way, because it's the only way to fix the proteins into this large pore size matrix and at the same time remove the Carrier Ampholytes, because you don't want to have the Carrier Ampholytes during staining, because they would give you a lot of background staining. Then the SERVA Violet 17 staining, I told you already, is the most efficient organic dye staining, and the ammoniacal silver staining, we have developed this for the cerebrospinal fluid detection, but it's also very useful for other applications, is the most sensitive, very, very sensitive silver stain. And a short comment also on Western blotting. Electrophoretic blotting is a little problematic always after isoelectric focusing, because the proteins have no net charges. They are at the isoelectric point, and so there are also papers around, and we have tried it, that pressure blotting is really the method of choice for this. There is a paper in the journal Electrophoresis from the year 2001 that was published by Harry Taubin, who, by the way, is the inventor of Western blotting. So his first very famous paper comes from the year 1979, and he's working at Novartis in Basel now, and he also has found out, or he was the first to find out, that pressure blotting is the method of choice for isoelectric focusing gels. Here you see a very high sensitive silver staining of an isoelectric focusing gel, basic gel 6 to 11 with 24 sample wells. And this was what I wanted to tell you. Thank you for your attention.